joining in person and in Zoom. Today, I'm honored to have Professor Powell in the seminar. So Professor Powell is an associate professor here at WPI, joining in 2018. He has authored 8 publications, gave 12 invited presentations, filed 2 invention disclosure, and raised more than $4 million for their research in sustainable metallurgy. Prior to that, he has been the Chief Technology Officer and the co-founder in the Infinium. And prior to that, he has been the principal at Open Innovation, managing engineer at Veris, and then a professor at MIT, as well as a metallurgist at NIST. His prior education, he has his PhD from MIT at 1997 and his bachelor's in 1992. So today he will talk about the innovation for climate impact methods and projects of the Energy Metal Research Group. So thank you so much.
These are the publications and fundraising since I've been at WPI. So that on either way. All right, it's a pleasure to be here, and let's see. So let's take just a moment. Let's go to go and HDMI and oops. Share. Okay, all right, so it's good to be here. We're talking about innovation for climate impact, the methods and projects of our research group. So I have a long list of different projects to present, but to talk about. But in addition, I think what I'd like to highlight is where some of these projects come from. So I think my favorite slide in Bob Hires' talk when he was doing his department head interview talk was where he talked about how different projects come from the boundaries of research fields. They come from some from spontaneous ideas, come from a variety of different places. And then he had a last category of impact, that is impact on the world. He said that's really hard. And it occurred to me as he presented it in the seminar a couple of weeks back that that's what we've been trying to do in our research group. And so I'll talk about how the different influences in my life come together and in our research group to create these different projects. So to begin with, begin with a dedication. Dedicate this talk to 4 people. First, Julian Sekeli. You may recognize a couple of people in this photo, maybe the guy in the black shirt, but also on the left side, that's Bob Hires, our new department head. We were in the Sekeli research group together. It's a real pioneer in the application of chemical engineering methods to the metals industry. Very prolific author, numerous books, publications, hundreds of publications, and a wonderful mentor, just incredibly gifted intuition, etc. Second is Uday Powell, who we will hear from in the spring. He became my PhD advisor after Professor Sekeli passed away. And he has been a mentor ever since then. His invention of the zirconia solid oxide membrane anode is part of our current research, as well as the kind of technical signature technology of my startup company, Infinium. So Donald Sadoway, we heard from recently. He also is a pioneering electrometallurgist. So I get many methods and ideas from the way that he's done research. Took graduate electrochemistry from him. He was on my thesis committee and has been a mentor since. And finally, Tom Eager. Tom was the first person I met out of this group in sophomore thermodynamics. He kept in touch over the years, and when I was founding a startup company, a co-founder and I came to him to ask him a technical question, and we had lunch with him. He brought a check. He said, "Here, I want to invest in your company." I said, "Wait a minute, we don't have a mechanism for doing that, but we'll figure it out." And so he was the first investor in Infinium. He knew very little about the company or about what we were doing, but he really believed in me, and I can't thank him enough for it. Just received news a couple of days ago that he passed away on Sunday evening. He had a fall, and although I've gotten together with him a couple of times a year, he was very involved with our company in the last couple of years. It's one of those things that wakes you up, because I wish I spent more time with this person. So I'm making an effort to spend more time with my mentors, and really dedicate this talk mainly to him. But I'd say that the four of them really together taught me, within my field of materials, the value of metals in particular for their very high performance, their recyclability, their just many aspects of metals and the environment, the importance of producing them in a sustainable way, and some of their potential uses in energy devices beyond metal production and recycling, et cetera. So really want to thank the four of them. So I'll start with the first project in our group, solar silicon production. This is the project of Aditya Mughal, a PhD student, but in addition, a collaboration from Uday Pal and Yu Zhang. So this began with Uday's technology on solid oxide membranes, which I'll talk about in a moment, and the goal of using that to influence clean energy became one of the first ideas at Infinium. We would look at magnesium and also at solar grade silicon. It turned out that there were some challenges that hadn't anticipated, and there still are. It's a tough chemistry. The idea is that instead of going through this complex process from carbothermic reduction of magnesium, metallurgical grade silicon, getting ahead of myself, conversion to chlorosilane and chemical vapor deposition, that every gram of silicon used in every solar panel gets made into trichlorosilane, distilled, and CVD. It seems kind of ridiculous. So others have proposed things like electrorefining. This is the Sadoway's 3-layer electrorefining process. But what if we could eliminate the carbon and just go directly from silica to a higher purity silicon? That a lot of the contamination comes from that carbon. We go from 99.8% pure silica to 98% pure silicon, metallurgical grade silicon, because of that contamination. And then we have to get that contamination back out again. So that seems kind of strange. Why not just go directly from silica straight to a higher purity silicon product? And the imperative to this is that silicon is a relatively small fraction of the cost, about 15% for the last 20 years. However, if we're going to continue to drive down the cost of solar energy to 18 cents, 15 cents, 10 cents and beyond, our current 4 cents per watt won't do it. And there's really no more room to reduce the cost of Siemens processed silicon. So the idea is to dissolve silicon dioxide in a molten salt bath. And in particular, the work of Uday Pal over the last 12 years or so has led to a new molten salt bath chemistry that was an order of magnitude better than everything else in 5 key metrics: solubility, the conductivity, viscosity, volatility. And so this allows you to dissolve silicon dioxide and use a zirconia, yttria stabilized zirconia solid oxide membrane anode. So this electrochemically pulls the oxygen from our molten salt electrolyte through a solid zirconia electrolyte into an inert anode where it becomes oxygen gas. At the silicon side, we reduce, it's not really Si4 plus, it's more like an SiO4 4 minus, but it's silicon in the oxidation state of 4. Gets reduced to silicon, which at this temperature is actually a decent conductor of electricity. And we suppress dendrites by periodically switching one or more of the cathodes to an anodic state. So instead of depositing silicon, we're dissolving it away from the surface. And so this is a process that I've been working on for quite a while. The big payoff is the energy reduction, 90% versus the Siemens process, let alone the much greater simplicity. A single step or maybe 2 steps from raw silica out of the ground to a silicon process you can use. This is what it would look like scaled up, making silicon slabs with the zirconia tubes, and a larger high current cell would look something like this. This is the energy balance, the thermal energy in versus the voltage voltage stack, the energy. 2 different kinds of energy: the free energy and the thermal energy used to reduce the silica. A techno-economic model shows $1.74 per kilogram operating cost. This is considerably lower operating costs and capital costs, but nonetheless a very high cost for a plant. So a big barrier to entry, but significantly lower than the lowest cost today of about $8 to $10 per kilogram. As I said, with very little prospect for getting it lower because of the fundamentals of energy costs. Next project to talk about is direct carbon fuel cell. So the goal of this is that bioenergy with carbon capture, the utilization of storage, has been a necessary part of all of the intergovernmental panel on climate change scenarios. But it's very inefficient that you have to first take your biofuel and your air. You have to do air separation and do some gasification in order to feed it into a fuel cell with an overall flow sheet with some 10 or 15 different unit operations and an efficiency around 30 to 35%. So about 8 years ago, Boyd Davis from Kingston Process Metallurgy came to me and said, "Hey, Adam, I have this idea. The coal industry is struggling with their emissions. What if we could just dissolve coal in liquid iron and then just use a solid electrolyte and make electric power that way. Just use air on the other side of the electrolyte, and so we took this idea. We wrote a couple of proposals, neither of which succeeded. But then this is while I was at Infinium, came here and picked it up, working with Uday Pal and Yu Zhang. Christian Faria, master's student, ran with it, as did Hung Yi Sun. And mainly Christian Faria, I'm sorry, Stephen Jasek is the second master's student. In any case, so Stephen Jasek was able to produce an electrode structure with just a 40 micron zirconia layer. So finally able to realize some of the performance. And this is the apparatus. Here's the cathode with the porous cathode with the zirconia coating. Here it is in the furnace insert and the furnace itself. And he was able to measure an open circuit voltage starting at 1 volt, declines slightly over time, maintained mechanical integrity with no significant degradation of the electrolyte. We were not able to measure the current accurately, unfortunately. And then he finished, and we've had well, we just leave it at that. But the open circuit voltage that he measured is very close to the theoretical open circuit voltage. Carbon is one of those things where the C plus O2 to CO2, the entropy is very close to zero. So the free energy and the enthalpy are very close to each other. And so we get a voltage versus current density prediction that looks like this. It declines as you increase the current density because the resistance the resistance losses are proportional to the current density. So you start from your theoretical and decline from there. This orange curve is the power density, and so you can see that we have a number of different heat losses, and the maximum voltage that we can get out of this while staying in thermal balance, that we don't just lose power and the cell cools down and freezes, is about 65%. With the final efficiency around 60%. This is around twice the efficiency of the integrated gasification designs, whether with combined cycle or a fuel cell. So quite a bit more efficient. And being able to demonstrate the high open circuit voltage indicates that we should be able to get that from this process. So this is an ongoing project. The operating cost is quite a bit lower as a function of the efficiency, and the capital cost as well. And that's because we have just basically 2 unit operations here. We take biochar that's or charcoal that's just produced by pyrolyzing your biofuel, your biomass. You can't really put it into any other fuel cell. It's just carbon. We think that we can use a lot less kind of theoretical energy per kilowatt hour of delivered energy because of that high efficiency. So this is an exciting project. It's still in progress, but again came from a collaborator. The next several projects deal with magnesium and magnesium metal in particular. So why magnesium? Because it's very energy dense, theoretical efficiency of 7 kilowatt hours per kilogram here, which is comparable to coal, but higher in kilowatt hours per unit volume, per energy per unit volume than any of the fossil fuels. Much better than ammonia and others we'll come back to later. It's very abundant. The oceans have 2 quadrillion tons, which is enough for 300,000 tons per human on the planet. We can take 1/1,000,000th of what's in the oceans. That's 300 kilograms per person. That's enough energy to deliver 1 month's worth of electricity consumption for the average US citizen. That's household, industrial, commercial, everything. It also has very low toxicity. We drink magnesium hydroxide for upset stomach, and we dump hundreds of tons of it per year on our roads to melt ice. And it reacts with CO2. I'll get back to that last point in a moment. But first, we'll talk about called the magnesium clean energy ecosystem vision, and it begins with production from seawater, as I mentioned. That every seawater desalination plant in the world that produces fresh water also has a concentrate byproduct that's mostly sodium, but the next most abundant cation is magnesium. And so a simple pH shift using, for example, sodium hydroxide for chloralkali cell precipitates magnesium hydroxide, which you can dry and calcine. So with electricity and in principle 0 direct emissions, you can go from this waste product to magnesium oxide. You can then take that magnesium oxide and reduce it to metal through a process that's been influenced by Uday Powell, who began well before Infinium, looking at the use of this solid oxide membrane to make magnesium. The next important piece of this came from David Dussault, who was my first master's student when I was on the faculty at MIT. After leaving MIT, he developed this process for vapor compression distillation of water, and got it to very similar efficiency to membrane separation of water from whether it's brackish water or seawater, the things. And so that was the inspiration for this. What if we could do vapor compression distillation of magnesium? Well, what we could do then is we could use what's called a reactive metal cathode. Start with something like tin, and that enables us to do molten salt electrolysis in the same way that aluminum is made today. And it enables this because once we've reduced a bunch of magnesium oxide to metal, we basically take 90-10 tin magnesium, increase the magnesium content, and produce oxygen gas, and then put it into this distiller and get out pure magnesium metal, and then tin with a little bit of magnesium left in it. So we get the pure magnesium metal out of that. So this is the work of many undergraduate students, and now Zujian Tang has joined our group to just joined us as a PhD student to work on this process. So I'll talk a little bit about compression distillation. So David Dussault, so basically the idea is that the energy of condensation provides the energy needed to evaporate your material. And this sounds like a perpetual motion machine. That's because, as described here, it is. You need a compressor to compress the vapor so that the pressure in the condenser is higher than that in the evaporator. Therefore, the boiling point in the condenser is higher than the evaporator. And the hotter condenser transfers heat to the cooler evaporator. So David Dussault was able to demonstrate this for a water system with input energy that's only 2% of the vaporization enthalpy of water. So the other 98% of the energy in this comes from the condenser. So a really impressive system. So he said that was the motivation, the inspiration for doing this with magnesium. So it turned out compressing magnesium vapor is really hard, but the next best thing is something called a multiple effect thermal system distiller, and we came up with something called gravity-driven multiple effect thermal system. This is what that looks like for a 100 kilogram per hour distiller. On the inside, we feed scrap or our magnesium tin alloy, and it flows from the melter to the first evaporator, where some of it evaporates and condenses up here, and then what remains flows down to the second evaporator, where some of it evaporates and condenses. So what remains flows down to the final evaporator, where some of it evaporates and condenses, and remainder flows down to the concentrate accumulator. So we end up with, we start with something that's, as I mentioned, say 90%, no, 50-50 by weight magnesium tin, which is about 85-15 by mole, and more magnesium moles because of its molar mass. And we end up with something that's 90% tin by mass coming into the concentrate. And the energy from condensation provides the energy needed to evaporate in the next effect. And this energy from condensation here, it provides the energy needed to evaporate in this top effect. And the pressure differences are created by these standpipes. The liquid height, your rho GH gives you a higher pressure in this evaporator 3 than above it, a higher pressure in evaporator 2 than above that, etc. So even with the effects of the solutes, your tin in this case, or alloying elements for recycling, or neodymium if you're recycling, if you're distilling magnesium from a a rare earth magnet concentrate, you can still have a higher condensation temperature than the evaporation temperature at the next effect, quite a bit higher, and you're limited by heat conduction from that condensing surface to the evaporating surface above it. So the model shows this uses about 1/3 of the enthalpy of vaporization as the input energy. In practice, small scale in the lab, we've been able to get 2 kWh per kilogram, which is just over the enthalpy, and about 60 to 80% less than the 5 to 7 kWh per kilogram used in industry today. So that's the basic how the technology works. You can scale it up just by making it wider, and so that's the process. Next, we can use this for many different applications. I mentioned that the metals have high performance. Magnesium has the best strength to weight and by far better stiffness to weight in parts than other metals, and is far more recyclable than composites. So when Ford and Magna looked at what would the ideal multi-material lightweight vehicle be, they chose composites for some part of the substructure, but for the exterior and a lot of the structure, they chose magnesium because it's just much more expensive to make composites into the Class A surfaces. The cycle time in the dies is very high. You need very large numbers of dies. It takes a half hour or more, whereas magnesium, it's sheet stamping. It's seconds per part in a stamping die. So one of the biggest challenges is joining and corrosion. And so as I was transitioning from Infinium to WPI, I talked with Tim Scheck at Magna, who said, we've got this new lightweight door that we're looking at, and we want to, instead of making it all aluminum, we want it to be aluminum magnesium. But we're concerned about corrosion at welds. And so I worked with, my next call was to Brajendra Mishra, who was a corrosion expert here. And then we put together a group, a postdoc and a grad student, and a group at Pacific Northwest National Lab and Oak Ridge National Lab. And we worked on understanding corrosion at welds. So that project is wrapping up now, and we've shown that the friction stir welds have very little corrosion, and we think we understand why based on the some of the structures that form and their electrical potential. We're finalizing that more on that another time. But the next project is on rare earth magnet recycling. So this is something that has been around for years. A group of Toru Okabe at the University of Tokyo, another colleague, pioneered this, and Hitachi picked it up. But the issue here is that you can leach the rare earth metals out of rare earth magnets using liquid magnesium. However, then you have to use distillation to get the magnesium out. As I mentioned, that's a very inefficient process. But if we use GMET's distillation, Chinenye Chinwego has shown that we can cut the energy use by about 60% and the cost by roughly in half using our distillation process. And to get the last bit of magnesium out, you have to go to vacuum distillation, but you've already removed about 80 or 85% of the mag much more efficiently than this conventional distillation process. So she's in the process of starting a company and raising funds. So it's exciting. This may be the second spinoff, second to Solar Silicon of Aditya and Mohammed Asadikia. And so next is a molten salt magnesium air battery. This is a large team. It's started by Hong Yi-sun and led now by Maya Shahabi in the group. I'd say that this is one of the two projects that really originated within the group. The idea began with Hong Yi working with Christian Faria on the direct carbon fuel cell. And we thought, okay, what if we put some liquid magnesium on top of this, that as the CO2 came out, the magnesium would grab the oxygen and oxidize, and the carbon could go back into the liquid metal. So we'd have kind of a closed loop, carbon, CO2, back to carbon to CO2. The magnesium would turn into magnesium oxide, and we could use its extraordinary energy density to maybe propel ships across the ocean. Well, that was a terrible idea because a lot of energy is lost in that CO2 plus magnesium to magnesium oxide plus carbon reaction. You only get about a third of the energy out of it at most. So we went back to the drawing board and we said, okay, what about aqueous magnesium air batteries and fuel cells? Those have been around for a while. We looked at the literature and we said, this has some fundamental problems. You get an oxide film that passivates it and stops the reaction. We get hydrogen evolution. And so we're really not equipped in this group. We don't have the core competencies to deal with that. What else can we do? What about a molten salt? How would you do a molten salt metal air battery? And we came up with this this idea, this crazy idea. You just put the magnesium, attach it to an electrode, and have an air electrode at the other side, and generate a voltage. Is that going to work? I had no idea. So we tried it, and not only did it work, but whoops. Skipped something. All right. Anyway. All right. So we were able to generate 1.9 volts, which is the highest voltage of a magnesium air battery to date by far. The next highest is 1.4 volts. So that was Hong Sun's work. So the way it works, as I mentioned, we inject air into a porous cathode. It can be made of nickel, titanium, or stainless steel. And we found that for many hours in air with a molten salt, nickel is just fine. It doesn't oxidize, let alone dissolve. So it's pretty remarkable. And as I mentioned, it generates a voltage through these combined reactions, oxygen to O2 minus, magnesium to Mg2 plus. And these two dissolve in from the anode and the cathode into the molten salt. So your overall reaction is just the oxidation of magnesium to MgO. The theoretical energy density is extraordinary. And the practical energy density is somewhere around 1,500 to 2,000 watt hours per kilogram, which is about 10 times lithium ion. Then the problem is you have to get this magnesium oxide out of the molten salt. So a proposal for that was, let's try freezing it from one side and see if that works. And sure enough, the first time Maya tried an experiment, it worked. We were able to see an immediate jump in the voltage due to a reduction of the magnesium oxide concentration and activity in the molten salt. So it was really exciting. And waiting for something to go wrong, and I shouldn't say that. Everything has gone pretty well so far. The operating temperature of this molten salt electrolyte is pretty high, though, and that limits us. So we can't scale it down because you would lose too much heat through the sides. So we think the minimum size is about a shipping container. This is a schematic in a 20-foot shipping container with a series of 10 anode cathode pairs in series in order to generate more voltage, which has various advantages. In terms of the material selection, as mentioned, magnesium has not only a high energy density. Aluminum and silicon beat it, but silicon halides are gases that would come right out of it. So that's not an option. Aluminum could be an option. However, its oxide scale is very stable, very low solubility. So you get passivation of the aluminum the way that you get passivation of magnesium in a magnesium air battery. Magnesium is a logical choice for these reasons. Theoretical density extraordinary. The chloride salt is basically dehydrated seawater plus carnallite, which is produced from the Dead Sea. So incredibly cheap. As mentioned, this open circuit voltage, the cost estimates for this battery are somewhere around $3 to $5 per kilowatt hour. This is extremely low. You're talking comparable to pumped hydro, where you pump the water uphill and then capture its energy downhill. The limitations, as I mentioned, are high temperature and a low round trip efficiency. So when you convert the magnesium oxide back to magnesium, you're putting in a certain amount of energy. You only get somewhere in the 40 to 60% of that energy back. So for round trip efficiency, lithium is much better, 90%. So if you can power something with lithium batteries, great. But for a ship, you're only going to go a few hundred miles. If you want to go across the ocean, it's just the way to do it, I think. Very low cost, very high energy density, and for potential electrification of ships and maybe aircraft. If we look at the figures of merit, the round trip efficiency is considerably lower than lithium ion or ambry, comparable to iron air of form energy, but with much better than ammonia, with not quite the energy density versus a tank full of a container for the ammonia tank. But ammonia is, of course, toxic and explosive, et cetera. Hydrogen as well, so much better energy density than hydrogen, better than ammonia, and very low cost as well. Also not as high a discharge rate, but when you're trying to get across the ocean, you're talking about hundreds of hours instead for a discharge, maybe tens of hours for a long distance flight. Our next step, we're working on demonstrating recharging in situ. It's an experiment this week. Well, not for recharging, but okay. Anyway, the final project I'll talk about is a magnesium hydride zero emissions jet fuel. It's a project with Jagan Jayachandran. And this came up when Jagan and I both started in summer of 2018. We were in new faculty orientation, and he was a combustion expert and talking about aviation. How do you clean up aviation? They're biofuels, but they displace crops and they displace wooded areas for carbon capture by forests. They're not very efficient. Corn ethanol, for example, has the same life cycle emissions as gasoline. Right, so it's what do you do? Well, let's think about metals, and there's the graphs that I'm showing of energy density and specific energy. Those came from a paper that Jagan found. And maybe metal hydrides. So we came up with a mixture of magnesium hydride and hydrocarbon fuel. Part of the inspiration for that came from a company called Safe Hydrogen, which is using a magnesium hydride mineral oil slurry for hydrogen storage. So you heat it up, and the hydrogen comes out. You heat it up under high pressure, and the hydrogen goes back in. But what if we just took this slurry and burned the whole thing? So kind of a crazy idea, not using mineral oil, but using a lighter hydrocarbon. We did some thermodynamic calculations, which we were just accepted by the journal Fuels. This will be our first journal publication on this, showing that for a given equivalence ratio, with 1 being stoichiometry, and 0.5 meaning that you have twice the air that you need, half the fuel, you get to a considerably higher temperature with magnesium hydride. And that means that you can, if you have a certain target temperature based on what temperature can your turbine handle, you can burn leaner using less fuel, more air. I mentioned that Jake Scarponi is here. He did some of the work on this, both the combustion tests, and also some of the research on atmospheric interactions in Yijie Wu as well. So for a given mass of this slurry, to reach a given temperature, you need a larger mass of the slurry than of the jet fuel, but not as much as you'd predict based on the lower heating value ratio. And that's because magnesium burns more efficiently. It holds onto the oxygen more tightly, whereas CO2 decomposes into carbon monoxide and oxygen. Water decomposes into hydrogen and oxygen. So you don't get the full energy out of it. And that's especially true at high temperatures, but even at lower temperatures as well. You have a lower mass ratio. And in particular, if you look at the volume, you use much less volume of your slurry, in the order of 15% less. And again, less than you'd predict using the lower heating value based on these complex thermodynamic calculations that Jake and Yijie worked on. It's great. All the students who've been leading these projects are right here today. So, so it showed us that for aircraft range, volume is more important than mass. That even though this fuel weighs so much more than conventional jet fuel, and dodecane is pretty much it's the single hydrocarbon or the simple hydrocarbon that's closest to jet fuel. You end up with 8% more range if you put the same fuel into a 787's fuel tanks, and especially much more range than with ammonia or with hydrogen. Of course, you can't put those into the fuel tanks because they have to be either pressurized, which today's fuel tanks are not pressurized fuel tanks in aircraft, or cryogenic, and same thing. You can't. So considerably better range than either ammonia or hydrogen for aviation. Of course, the higher weight means that you'll have a heavier landing gear and wings and other structures. So probably lose that 6 to 8% better range and end up with comparable range. But there is no other solution today with comparable, a proposed solution for aviation with comparable range. Lithium batteries, of course, are way down here somewhere. So they're great for a couple hundred miles, but not for your transcontinental and intercontinental flights. So, so this is just a summary of the magnesium. It's safe, abundant, energy dense, and flexible for these applications. And I would summarize the talk by saying that how do these high temperature electrometallurgy innovations come? Number one, by networking. As I said, most of the ideas came from the outside, and we built on them in the group. Network and read. Brainstorm, focus on the key goals, like with the magnesium rare battery. Just, how can we do this? This doesn't work, this doesn't work, this doesn't work. Let's try this thing. What if it does? And sure enough, it does. And also a mission. One of the first things that we did with this group, we came in about 1 year in with Aditya and Cuba, the postdoc, others, is to put together our vision statement, our mission statement, and how we work, our core values. And important thing about the mission is not just what we do, but what we don't do. So this spring, I kind of reverbalized this as a gigaton rule, that we don't do projects that unless they have the potential for making significant progress toward 1 gigaton per year of greenhouse gas reduction. So with that as our focus, you can see focus way too many projects, even with that consideration. Yeah, we are working to innovate for climate impact, to try to make some industrially relevant and commercially viable technologies, all at the research stage now, but some of them coming out into commercialization in the near future, hopefully, as quickly as we can. So thanks very much, and I'll take any questions. Industrially relevant and commercially viable technologies. Sorry. What's happening? Sorry about this. Now, but yeah. That's the YouTube Still running. Stop that. Right. Okay, so take any questions now. Yeah. All right. Yes.
Very nice presentation.
Thanks.
Quick question. For the molten salt magnesium air batteries, I
Mhm.
see the sketch. Sounds like upon discharging, you fall magnesium oxide on the bottom, right? That
Yes.
sort of make it like primary battery operation. Right? You may not able to recharge.
That's the question. Yes. So there are two mechanisms for potential mechanisms for recharging. Yeah. So one of them is to, as you said, just at the end of life, dump out the molten salt, take the magnesium oxide, and send it back to the reduction plant. So that's one option. Another option is to instead of cooling the magnesium oxide side, we heat it so that it dissolves into the molten salt. If we can stay close to the solubility, I think we can get somewhere around 0.1 amps per square centimeter of reduction current density. So we're going to try to reverse the cell and go from dissolved magnesium oxide to magnesium metal. This is not the ideal electrolyte for that. The solubility is only about half weight percent. We can potentially add fluorides to increase that. We're trying to avoid it to keep the cost down. So we're going to try this and see how well it works with an oxygen producing, we call it the positive electrode. That's what Sadoway said, right? It's not anode and cathode because they switch their roles between charging and discharging. If that works, then we'll get up to something like we think the 60% round trip efficiency. If not, then we'll probably be closer to 40%. And the nice thing is that you can do a multipolar oxide reduction cell, which has never been done before. There's meaning multiple cells in sequence in a single molten salt bath, just by reversing the battery. So that's the concept there. So there are chloride electrolysis cells that use this and are very efficient, close to 80% efficient. But first you have to produce the anhydrous magnesium chloride, and that's another can of worms. So another issue. So very expensive. Other questions? Yeah, this was the slide that was accidentally skipped. I'm not quite sure how, but yeah, that's the evidence diagram here. And the neat thing is that we have this nice gap between the enthalpy and the free energy. So we can lose a lot of heat and still run very close to the maximum free energy. Yeah, this is 3.1 volts, not 1 volt. So that's why we can potentially lose all of this heat. We did this after doing the carbon fuel cell models. Like, wow, if this can work, that'd be pretty cool. So, all right, I'll take other questions. Yeah, and here's what we achieved: 1.9 volts, which is close to the 2.3 theoretical. All right, maybe I'll just finish presenting this slide. So no other. If we can follow this model curve, then we can get to 80% efficiency. As it is, this is about 60% efficiency, and that would correspond to about 90 megawatt hours in a shipping container, compared with the best lithium-ion battery, which is 4. So 20 times more energy. So if you were recharging your ship by swapping in these containers, you could go 20 times farther per container with this battery if it works. Yes.
That was very impressive, and I wish I could think of a technical question. But I think I might have understood some of your last slide. And the brainstorming. And, I'm wondering, And that's, one of the things I'm talking about, writing about. It seems like there's a lot going on.
A lot of borrowing, a little bit of original ideas.
It might be fun to talk about that sometime.
Great.
In the context of design.
Yeah, I can't say that we've come up with any kind of unique formal process for brainstorming, and there are all kinds of, there's all kinds of literature out there on different mind mapping and various things. But yeah, like I said, I think just network, read, and just struggle with it for a while, and you get to come on and focus, and you get some ideas at least that will hopefully work.
So I'm trying to put this into the things that I've been working on, like the axiomatic design and the decomposition. Much to generate.
Sure, yeah, that's true. But
How to treat them.
but within each one of these, there's 10 different decisions to make.
So separating out functions.
Okay.
And physical.
Okay.
Fulfillment. That's fine.
Mhm.
So in your brainstorming, are you looking at like functions that you're trying to achieve and maybe physical ways of doing it, or it's
Yes, basically. Yeah. So for the magnesium air battery and the aviation fuel, it was yeah, these hydrocarbons are just so energy dense. What do we have that comes close?
yeah, the high level, I guess.
Yeah.
But so when you're figuring out this solve that, is that also functionally based, but a much lower level function than replacing?
Yeah, good question. I guess so. Yeah. So in the aviation fuel, the functional requirement is really about generating high temperature. Well, within the context of a jet engine, it's a high temperature, and so yeah, as mentioned, aluminum has more energy, but it passivates more easily. Magnesium actually evaporates at these engine temperatures, so it can burn in the vapor phase, which is just neat. The hydride shatters, so going from micron size to very small. We're not exactly sure how, but the combustion particles are about 100 nanometers, the combustion product. So so we get more area vapor. Yeah, I guess. Yeah, it's. Yeah, but we didn't start with the thermo and say, okay, here are the different potential materials. Let's choose magnesium. We started with, okay, we have to get to temperature. We have to have a high energy density. What do we use? Maybe metals, and then maybe metal hydrides. And
So that's kind of function based.
yeah, I guess so. Yeah,
It's a function.
Yeah. That's true. The temperature at low weight. Oh, yeah, I'd love to. Yeah, it makes a lot of sense. I'd love to sit down and try a decomposition. That's we had an MQP group actually do something like that for the silicon project, and that was that was really neat. Showed much greater alignment between the design and functional than than today's Siemens process. So that was neat. This idea of doing chemical vapor deposition to produce a metal. Then again, distillation to produce a metal seems strange too. But if you can do it efficiently, then and with a relatively simple and low cost apparatus, then that's what we're trying to do here. So yeah. But I'll mention, yeah, for magnesium production, if we can recharge these batteries then we can feed magnesium oxide and make magnesium from the MgO from seawater, probably a lot more cheaply than with the zirconia some electrolysis.
So if we could do that with seawater, I think what we could do is good pot.
Question. Oh, yes. Is there going to be a form to track track attendance? The only generic one we've got. Sure, why not? Okay, the other, I didn't make a specific one for this this talk, unlike last time. So I can't say compete with Sadaway, so not expecting any of the last answers, but all right. Yeah, I'll be able to download that poll a bit later. Or okay, great. Well, thanks very much. I think we're about all set, and appreciate coming, and forward to continuing to work with you all. Thanks. All right.